Hello, welcome you all for the third video lecture of Strength of Materials.
I will take the example of small bar of some cross section A. A is a cross section of the bar, and I'll subject this to a axial load like this of magnitude P. Let us say you cut this bar here and try to write the left portion separately. The left portion I'm writing it separately like this. Now this end of the left portion is having the external load P, but on this cut surface there will be internally distributed forces which are developed because of the inherent property of the material. The material, when it undergoes deformation, it tries to resist the deformation by developing these forces. Since this portion also is in equilibrium, internal force should be equal to P. The intensity of internal forces in the material against deformation or external load is called stress. Similarly, I can show the right portion also. This is the right portion. This is the applied load P, and internal forces will be in the opposite direction like this, and total magnitude of this internal force should be equal to externally applied load P. Now mathematically, intensity of internal forces is defined by the ratio of total resistive force and total area of resistance. So stress is denoted by the letter sigma. Total resistive forces developed divided by the total area of resistance. So for this bar now, applied load is P and total resistive force developed is also P. Area of cross section or area of resistance is A. Therefore, stress sigma can be written as P by A. So if the load is in Newton, if the area is in meter square, the unit is Newton per meter square. Sometimes we will have to express stress in terms of Newton per millimeter square also. You know that 1 Newton per meter square is 1 Pascal. Kilopascal is 10 power 3 Newton per meter square. Megapascal is 10 power 6 Newton per meter square. Gigapascal is 10 power 9 Newton per meter square. Sometimes we will come across 1 Newton per millimeter square. We will have to express Newton per millimeter square in terms of megapascal or Pascal. So 1 Newton per millimeter square is equal to 1 Newton by millimeter is 10 power minus 3. It becomes 1 into 10 power
Whole
6
square.
Newton per meter square. 10 power 6 Newton per meter square is what? Megapascal. 1 Newton per millimeter square is equal to 1 megapascal. Next, we will see types of stress. The first one is called direct stress or normal stress, or it is also called longitudinal stress. When I have a bar like this, it is subjected to a load P. This is called direct load. Load which is normal to the end face, it is called direct load. So if the cross section area here is A, then normal stress is sigma is equal to P by A. This is called direct stress or normal stress, which can be compressive or tensile. If I reverse the load like this, if I make it P like this, then sigma is equal to P by A. It will be taken as minus here because it is compressive. It tries to reduce the dimension of the bar. Since it is compressive, negative sign is used. So this is compressive stress, and the first one is called tensile stress. So direct stress can be tensile or compressive. So direct stress can be defined as the stress developed or intensity of resistive forces developed inside the material against the direct normal load applied. Second type called tangential stress or shear stress. In the previous case, if this is the bar, if this is the load, this load P is normal to the cross section. That is why we called it as normal stress. But tangential means it is along the area. Load, if it is along the area, then it is called shear stress. For example, the same bar, if I apply the load like this upward, this load is called tangential load. Here also you can define stress as load by area, but the load is not normal to the area of cross section. It is tangential or shearing. So it is called as shear stress or tangential stress, denoted by the letter tau. So shear stress can be defined as the stress developed or intensity of resistive forces developed against the tangential load or shear force. You take a plate like this, it is fixed at the bottom face, let us say like this, and you try to apply a force like this. This is P. Opposite side there will be a reaction force which will be opposite to the applied force like this. That is also magnitude P. So if you divide this P by the area where you are applying the load, the top face, then it becomes a shear stress. So this is one of the example. We come across riveted joints in mechanical engineering application, joints which are made by using rivets. I'll just show you one such example. This is how the rivet look like. This is plate 1, this is plate 2, and this is the rivet. In riveted joint, plates are subjected to loads like this. Now for the plate, if you consider this end surfaces where the load is applied, it is normal direction only. So if I define P by the normal area here, it is normal stress only. But if you consider the rivets, I'll just show you the cut section of the rivet. This portion, I'll write it separately here, and top portion only I'll write. Top portion, half of the rivet, top plate is like this. This is the bottom plate. The applied load is P here. So at this surface, at the bottom center of the rivet here, tangential force will be there like this, opposite to the applied force P. That P divided by the cross section area of the rivet. Rivet cross section will be circular. Diameter is D. So area of cross section of the rivet is pi d square by 4. So shear stress will be equal to P by pi d square by 4, P by A. Since the load is tangential to the cross section of the rivet, so we call stress P by A for the rivet as shear stress. Next, to define
This is
what
also
strain.
called as a
Strain
case
is
of single
actually
shear.
the measure of deformation caused by the load on the material. It is a measure of deformation, which is the ratio of change in dimension to the original dimension. So this is the general definition of strain. We can write different types of strain. We have seen normal stress, shear stress. Similar to that, we can also classify strains as normal strain, shear strain, volumetric strain. I'll take the same bar example now. I'll take a circular bar like this, subjected to load P on either side. Let us say the original length of this bar is L and the original diameter of the bar, I'll call it as capital D. After application of load, it will undergo deformation. I'll write the deformed shape like this. The length will increase by a small amount. After deformation, the total length, I'll call it as L plus DL. What is DL? DL is a change in length. Now, we will come back to the definition of strain. Strain definition is ratio of change in dimension to original dimension. Now, in this case, the change in dimension is what? DL divided by original length is what? L. So, DL by L is the strain, which is called as linear strain or axial strain. So first type of strain is called direct strain or axial strain or normal strain or longitudinal strain. All these terms are same. So axial strain is dl by L, change in length divided by original length. We will also observe that the diameter is also changing. When I elongate this bar, diameter is getting reduced, length is getting increased, but the diameter is reduced. So I'll call the new diameter as phi of d minus dd, because diameter is reduced and reduction amount is dd. Small dd is amount of change in diameter. Now in the diametral direction also I can define strain. So strain is equal to change in dimension by original dimension. Change in dimension means change in the diameter, which is dd, and original diameter is d. So this strain is called lateral strain. Epsilon is the symbol used for designating strain. For lateral strain, it is epsilon lateral. So we have defined the lateral strain, second one. So what is the definition of lateral strain? Ratio of change in lateral dimension to the original lateral dimension. There is a special property of any material which says that the ratio of lateral strain to the longitudinal strain is a constant. It is experimentally observed that lateral strain divided by longitudinal strain is a constant for any material, which is called as Poisson's ratio. This is again a very important definition. Poisson's ratio is defined as the ratio of lateral strain to longitudinal strain. So Poisson's ratio is denoted by the letter nu. Steel has a Poisson's ratio of around 0.3. It varies depending on the composition. Aluminium will have a slightly different value of Poisson's ratio. It will be 0.25 to 0.27. Third type of strain, which is called shear strain. It is denoted by the letter gamma. For example, if I take a plate like this and fix the plate here at the bottom edge and subject this to a load like this, shear load. I'll get shear stress. I'll write it as tau. But how does this plate deform? It deforms like this. There is an angular movement now. If you observe this left vertical edge and right vertical edge, they are rotated about the bottom point. So there is an angular deformation. So that angular deformation is called shear strain, gamma. If this distance is L and if this moment is dl, we know that for small angle, tan of gamma is nothing but gamma, which is the ratio of dl and L. So shear strain is the angular deformation produced by the load expressed in radians. Fourth one is called volumetric strain, which is denoted by the symbol epsilon suffix v. We know that generally strain is defined as the ratio of change in dimension to original dimension. So when we define volumetric strain, it is defined as the ratio of change in volume to the original volume. So epsilon v is the ratio of change in volume divided by the original volume, or dv by v. Now we will try to relate stress and strain. So there is a law called Hooke's law. Hooke's law says that for all elastic materials, stress is directly proportional to strain within the elastic limit. According to this statement, stress is proportional to strain. So stress can be written using a constant which is called E, and this E is nothing but Young's modulus, or it is also called as modulus of elasticity. What is the unit of strain? This is unitless. What is the unit of stress? Pascal, megapascal, or whatever. So Young's modulus will have the same unit as stress. Now this Young's modulus is very important for engineers because this is also a material property. I said Poisson's ratio, the ratio of lateral strain to longitudinal strain, is a constant, it's a material property. Similarly, Young's modulus is also a material property. It depends on the material. So E for steel is approximately equal to 200 gigapascal. Similarly, for aluminium, it will be around 80 gigapascal. For brass, it is around 100 GPa. We are relating normal stress to normal strain. We can also relate shear stress to shear strain. Shear stress tau is proportional to shear strain gamma. And here, what is the constant of proportionality? It is called G. G is nothing but the modulus of rigidity. And you know that this is shear strain, which does not have any unit, or it will be measured in terms of radians, and shear stress has unit. So G also will have the same unit, Pascal or Newton per meter square. So this is Hooke's law for shear stress and shear strain. Now, based on this knowledge, I want you to try this. Your question is here.
A solid light alloy bar of 40 mm diameter is used as a tie rod or tie bar. If permissible tensile stress is 320 meganewton per meter square, determine the capacity of the bar. So it is actually a bar or rod like this. Tie rod means it will have a small cross section and its length will be more, and it is subjected to tensile stress, means it is loaded like this. Diameter of this bar is 40 mm. And permissible stress is 320 meganewton per meter square. What is the meaning of permissible stress? The induced stress should not exceed this. That is the meaning of permissible tensile stress. The tensile stress induced in this material should not exceed 320. It can be less than that, but it should not cross this 320 megapascal. Let us say the load applied is P here. We have to find out the capacity of the bar, means what maximum load of P the material can withstand. That we have to find out. By the definition of stress, we know that sigma is equal to P by A. Stress induced sigma is equal to P by A. But induced stress should not exceed 320. But it can be equal to 320 or less than that. As a limiting case, we will use 320 as stress induced. So I will substitute sigma as 320. On the right hand side, load is unknown. We have to find out the load. Divided by the area. Area of cross section of this bar is pi d square by 4 because it is a circular cross section. Like this. So pi d square by 4 is the area there. And what is d? D is 40. So pi into 40 square by 4 is the area. Equation, when you solve now, find out P, you will get the capacity of the bar. 402.1 kilonewton. This is the answer you get. Allowable stress is given as 320 mega newton per meter square, and it will be 320 into 10 power 6 Newton per meter square. It will become 320 into 10 power 6 divided by 10 power 6 Newton per mm square. So it becomes 320 Newton per mm square. So when it is given in meganewton per meter square, you just use it as it is because 1 meganewton per meter square is equal to 1 Newton per mm square. One more exercise. For the same capacity, if a hollow steel bar with internal diameter of 20 mm is used instead of solid alloy bar, determine its external diameter. For steel hollow bar, permissible stress is 150 meganewton per meter square. Now, there are two cases here. One case is solid bar. This is a solid bar with diameter equal to, I will say, d naught. And other case is same bar with a hollow cross section. Outer diameter is d naught only, but inner diameter I'll call it as di. Both are subjected to the load of same magnitude. First, let us find out what is the load that this first case can take. I'll call it as case A and case B here. In case A, what is the maximum load of P that the body can take here? So case A, if you consider, stress is equal to P by A, and in place of stress, I can substitute 150 because that is the maximum stress the material can stand. So I'll substitute 150 for sigma is equal to P is unknown, I'll find out, divided by area. Area is pi into d naught square by 4. So I can find out P here in terms of d naught square. For the second case, he says for the same capacity, means both the members are subjected to same loading or both are capable of withstanding the same amount of load. So for the second case also, P whatever you obtained in the first case, the same thing can be used. But inner diameter of this is given as 20 mm. I will write the same equation, P by A. Second case also 150 remains here because for both the materials, material is same, so permissible stress will be same. That should be equal to P divided by A. A for the second case is pi into d naught square minus di square, which is 20 square divided by 4. But P is obtained from here. You substitute that P here, whatever you get in terms of d naught square. This becomes d naught square minus 20 square by 4. Now you can solve this. Only d naught is unknown and you can find out what is d naught. Just try to solve this. You are supposed to get this as 61.75 mm. To handle or to withstand the same load between a solid bar and a hollow bar, outer diameter of 61.75 is required when internal diameter of the hollow bar is 20 mm. That's the meaning of this. This is just to understand the concept of stress.